lead to fuel, reducing transportation dependency on oil. Today, transportation is an indispensable commodity for society, without which the society would become rapidly paralyzed and cease to exist as we know it. The dependency on fossil fuels is an acknowledged major weakness because these fuels have limited availability and are replenished just in geological timescales of hundreds of million years, thus are not renewable in the common sense. The distribution of oil resources is highly uneven, resulting in problems of supply that sometimes degenerate in severe crises and confrontations, including war. Recent survey suggests that current biofuels brought us to another dead end, because they are also dependent of fossil fuels. Our proposal for reducing transportation dependency on oil consists in obtaining liquid fuels from biogas resorting to thermochemical synthesis processes. Most of produced biogas is to be converted in liquid fuels, and the remaining stored as strategic energy reserve, making good use of the already existent natural gas network. This is done in regional units, which are composed of anaerobic digesters for biogas production, coupled with the conversion processes to liquid fuels. The feedstock of organic matter is supplied within a range of 50 kilometers or an 8,000 square kilometers area. Integration of processes, feedstock supply, and transportation network is determinant for operation cost reduction, and so for the success of this scheme. The estimated number of units for US 48 contiguous states is of about 1,000. Here we can see the process concept. The organic matter feedstock comes from some already available sources, such as municipal solid waste and food industry waste, but mostly from undeveloped resources such as agriculture and forest residues and non-intensive energy crops. These sources make the influent for the anaerobic digestion, which yields biogas, a mixture of methane and carbon dioxide that is then reformed at 900 degrees Celsius over suitable catalysts, turning into a mixture of hydrogen and carbon monoxide known as syngas. This will be the feedstock for the Fischer-Tropsch synthesis, yielding a synthetic fuel. This is made taking the gas to 150 to 300 degrees Celsius at a 10 atmospheres pressure over cobalt and iron catalysts. The products exiting the integrated process fulfill three main categories: synthetic crude, composed mostly of liquid hydrocarbons and short-chain alcohols, biomethane for strategic reserve, digester effluent for use as fertilizer and salt corrective, closing the nutrient cycle. The effluent still retains a large amount of the initial primary energy. Thus, some of it can be used as solid fuel. A typical unit digests an annual average of 4 to 8 million tons of dry matter, yielding biogas energy of about 1.3 to 2.5 million ton oil equivalent, convertible to about 5 to 10 million barrel oil equivalent, remaining in the effluent 2.5 to 4.5 million tons of dry matter. As a prerequisite, the energy crops cannot compete with food crops for nutrients and water, should demand a minimum of soil quality, and ban pesticides. As crops that fulfill those requisites, we present some well-known grasses, sometimes remarkable weeds, like torpedo grass and Bermuda grass, as also some nitrogen-fixing grasses, like clover, for enhancing soil fertility. The southward species are aimed to degraded soils, making them productive again. It must be realized that annually about 200,000 square kilometers of arable land is lost for soil degradation and desertification. The low lignin content of grasses allows a more effective digestion and greater biogas yields per ton of dry matter when compared to woody biomass. Seaweeds are proposed for their ability to grow without land, easiness of harvest, and for phytoremediation purposes. The types of terrain intended for energy crops production are marginal land and rough terrain, fallow lands, forest ground, estuarine and nearshore waters, especially in high-nutrient runoff sites. Harvest and transportation must be as economical as possible, avoiding consumption of liquid fuels because these fuels are too valuable for wasting in biomass harvest. To achieve the lowest operation cost, the machinery must be automated and remotely supervised by a human controller. The power source must also be a local one, such as wind or solar, supplied through a docking station, fed by the nearby electrical grid or from a purposely built system. The harvested biomass is then mixed with water and transformed in a slurry in the nearby station, and then transported to the main unit by a slurry pipeline or riverine transport. The linkage between harvest and transportation means is made by road transport of electric type. The power sources for the whole chain must be mostly renewable electricity, and that should be coupled with its storage and recovery inside the main facilities. An example of the cost of grassy energy crops is given by a study made recently in Germany on mountain soils using current technology and fuels, achieving costs of 8 to 19 cents per kilowatt hour. A cost reduction of 50% is foreseeable, but the liquefaction only retains about 50% of primary energy, resulting in a fuel cost of 10 to 20 cents per kilowatt hour. That compares with today's 10-cent kilowatt hour for fossil gas or diesel. It must be stressed that these are conservative figures, and even so, the synthetic fuel cost is already in a near break-even with the competitor fossil fuels. Implementation of these processes will allow substitution of imported oil, better balance of payments control, maintaining the use of current technology to take advantage of a worldwide resource, and by last, curtailing greenhouse gas emissions. All that converging to an increase of strategic security. Strategic security leads us to greater geostrategic stability, a stable socio-economical environment, and allows a smooth energetic transition during 50 or more years. That, hopefully, will take us to a world with more peace, stability, and sustainability.